the basic working of the neural networks. And over here, what I'm going to talk about is the shallow neural networks, which are like really maybe even the most primitive version, but they actually go into almost any version of neural networks these days. GANs, transformers, ChatGPT type like things, convolutional neural networks, which are used for computer vision and stuff like that, and also even the new version, which is the capsule networks, by Jeffrey Hinton, and and also there is this new algorithm, which is the forward algorithm, but no, we are talking about the error bag propagation algorithm, which is the most primitive form of that. So this is kind of like the outline of the presentation. I'm just going to brief introduction and I'm going to talk about the connectionist models and try to explain this analogy between human brain, animal brains and neural networks, because of the fact that because neural networks are basically inspired from how animal brains basically work. And I'm just going to give two really basic examples of neural networks, which were some of the initial examples of neural networks. And then I'm going to talk about the perceptron and the linear unit and the sigmoid unit, and then the gradient cellular network. And I'm going to talk about the Bragg propagation algorithm a little bit, and then in doing so, I'm just going to give a flavor of the mathematics that goes into it, but we're not going to scare ourselves with the mathematics. And it's not scary, and you're just going to find that it's fun. This is basically the purpose of this presentation, to introduce the maths while also trying to say that it is fun. It's not something to be scared of, Anyways, to whom it may concern. Anyway, so in humans we have these kind of like neurons switch between 10 to the minus, they switch every 0.001 second, and number of neurons 10 to the power 10, which is a lot of neurons we have, and the connections per neuron. So we know about how our brains work is that we have a lot of neurons. Each neuron has of the order 10 to the power 4, 10 to the power 5 connections, and they kind of like communicate with each other by firing synapses and stuff like that. Scene recognition time is 0.1 second. And stuff like this. So these kind of like statistics about human neurons, the human brain. Whereas, basically, in artificial neural networks, what happens is that, once we have this kind of like knowledge about how brains work, so mathematicians or scientists thought that, okay, can we develop these neural networks in the form of a computer program and they can learn in the same way? The answer was not exactly to that scale, but we could do a miniature version. So what we could do is that we could have some kind of a graphical structure, which is like a neural network of the brain, but it does not learn like the brain works. It learns because we don't exactly know how the brain learns, but then they fit in some algorithm for learning, and that is what we're going to be talking about. So there is basically some correlates between the human brain, or correlates, or even you could say differences as well at the same time. So this is one of the most primitive examples of application of neural network. So we have a neural network over here which has an input image of 30 to 32, and then it has an output of 30 output units, and each of the output units is basically, whenever it fires, it says that, okay, you have to steer to this direction, and if this one fires, it says you have to steer to that direction. So it's kind of like, so wherever the output is high, your steering wheel actually moves to that direction. So this basically tells us about some kind of a heat map of, the hidden layers, and I'm going to be talking about that in a while. But this is one of the basic, very initial examples of neural networks, how they work. This is an application which is pre-convolutional neural networks. Nowadays we have convolutional neural networks, and they do a lot more than this in real time. But anyway, so this is kind of like, uh, you know, yeah, oh, sorry. And this is another example in which this is the head of Tom Mitchell himself. This is one of his maybe students. This is another Tom Mitchell had, and this is one of his students as well. So the idea is to, as you know, predict the head pose. So it is a very, very basic example. Nowadays, neural networks do a lot more than that. But then they achieved, some, 90% accurate learning head pose that recognized one out of 20 faces. So it could do, which was a big deal. Oh, we could do it, with those neural networks back then. So this is the structure of the neural network. So you have, I showed structure of the neural network in the previous slide as well as this. So over here, so these are synonymous for neurons. And these are connections which are basically, neurons firing signals to the next. So in terms of the human brain, but it's not a human brain really, So when you implement this in software, so you take a data structure which is like for especially for people for computer science background, it is a directed acyclic graph, So every neuron, so in the sense of graph, this is a node, and then there are edges between the nodes, and you should only go from one side to the next. There are no kind of like, loops over here, or there are no reverse edges, So the edges always go from here to there. So yeah, okay. Yeah, over here he just gives an example that what were the ways of different hidden layers at different times. It doesn't make any sense. We can come back to it some other day, some other time. That's what they mean, but this is very interesting. That the idea for me at least is that the waves begin to look like somehow like ghosts of those images, So so there is some kind of shadows in those. Maybe John is finding this interesting, So these are basically, so this is after the first epoch, first learning cycle, and this is after the 100th epoch, which is the 100th learning cycle, So, yeah. Application of neural networks. When should we consider that we could apply an ANN? This is an important question. Every AI guy who's seriously learning about AI has to take a course in this. When to consider a particular algorithm to apply over there. So when to consider ANNs. So when input is, let's say, high dimensional to see a real value. When output is to see a real value. Output is a vector value. Possibly the data is noisy. Form of the target function is unknown. Yes, this is a very important point. And I'm going to come back to this later on. If somebody has a question about what this means, I would love to explain this. Human readability of results is unimportant. You don't care. And you don't care about explainability of the model as well. You just want something to work, And you don't know how to get it working, you just throw a neural network, and it's, you get a solution, So examples of speech phoneme recognition. So in speech recognition, neural networks traditionally have been applied very heavily. They've had some really good, applications over there. He's saying image classification, this is old bit of slides, but I would say anything computer vision, these days. Computer networks go into that, medical imaging, and this is that. Financial prediction, this is like, time series forecasting. And I'd also like to add over here natural language processing, because all the natural language processing, once upon a time that used to happen using Bayesian learning, but nowadays, Bayesian is kind of like a counterpart of Bayesian learning when you're using sequential neural networks, recurrent neural networks. But basically nowadays, you leverage heavily from neural networks, for natural language processing as well. So it covers so many things actually, So where did the story begin? So the story began by saying that, can we have a model that can fit inputs to the outputs? So we have inputs and the outputs, and can we learn a model that is in between? It's a very basic. So this is the basic question, So we have the data, we have the inputs, and then we have the outputs. Let's say we have the images, and then we have the corresponding labels. Can we learn a model for that? The answer was, if you fit something like this, then you could get a pretty good model, uh, given that the underlying model is basically linear, if it is linear. So it is for the linear case. So it is the perceptron. So what it is doing is that you apply, just give the inputs from here, and then you multiply every input with a W, with a corresponding weight value. And you bring all the inputs multiplied by corresponding weights to this point, and then you just sum them up. And this is how it is written. W0 plus W1 x1 plus W2 x2 plus W3 x3, and then you get it. You get this, and this is kind of like a thresholding unit, which is basically saying that if this is greater than 0, we say it is 1. If this is less than 0, we say it is minus 1. So it is saying that, okay, let's say like we're doing some kind of an image classification job, which is a 2-class problem, in which, one of the images has dots and the other images has rabbits, and you say, okay, +1 for dots, -1 for rabbits, and you just, replace the dots and rabbits with -1 and -1 respectively, and you fill in a linear model. So linear model, you're saying that, okay, I'm just going to talk about linear model in a way, but it is saying that, okay, if it is linearly separable, you can fit in this model, and it's good. So, the point I'm trying to say is that this is where the neural networks began. It is just a linear model. It is just doing linear regression or linear classification. But this is how it began. This is the perceptron. It was given by Rosenblatt and also Marvin Minsky as well. He proved a few things about it back in the day. Okay. Yeah. Okay. So I'm just going to move. So I'm just going to move ahead. Yeah, the series of the perceptron is that, so let's say like you have data, you have the pluses are for, let's say, rabbits, minuses are for ducks, for instance, given our example, you can take any other example, and you say if the data is linearly separable, or you assume it is linearly separable, maybe it is not linearly separable, but you assume that, okay, I'm going to fit in a linear classifier. By linear, I mean a straight line like this. This is linear. If I had a curve, we couldn't say it is linear. Then it is not a line. It is not a straight line. You know what I'm trying to say. So either the data is linearly separable, or we assume that it is going to be linearly separable, and we fill in. And what the perceptron does is that it just fits in this line. What do you mean by that? It just sets the slope of this line and the intercept value in a certain way that it falls somewhere in between the data. It divides the data. Pluses are there and the minuses are here. Or if they are not completely linearly separable, then it tries to maximize the division. It says the maximum pluses are going to be on this side and maximum minuses are going to be on this side. So this is job. But it assumes that there is a linear relationship or a linear divider over here. Okay, so this is the perceptron training rule. It is saying that what it is saying is, so this is the key part. So it is saying that you have the data, and you try to learn the right. So over here, the job, the real problem is, So the real problem over here is that your model is fixed. Your data is fixed. All you have to do is to find the right values of W's. This is the learning. This is the learning challenge. This is what learning is all about. And in the perceptron and all over, in neural networks. So this is what the learning is all about. So the learning rule over here is, it says that adjust the W so that on every iteration after seeing the data, so you adapt the W to Wi is equal to delta W plus 1, whereas delta W is equal to eta T minus O xi. Okay, we don't think about it, but at least agree with me that this is easy to implement. It is not, if you had to write it in Python or anything, this equation is easy to implement. You know, just let's agree with this. You know, so and I'm not going to talk about what this means. You know, because I have to be careful about time as well. So it is saying T is equal to C of X. So T is the target value. Yeah, this is important. T is the target value, and O is the output of the perceptron. Okay. O is the perceptron output, and eta is a small constant which is called the learning rate as well. So it is a small value. So making have prove that it is going to converge. And I'm not going to talk right now about what convergence means, but we'll talk about that as well. So how do you learn it? So in order to learn the values of W, one of the things that is important to understand is known as something that is known as an angular surface. So over here, this is a graph. So this is a very important idea. So this is a graph, and on the two kind of like dimensions on the ground, we have on one axis we have W1, and on the other axis we have W0 or any other W, which is basically the coefficients on these two axes. And on this axis towards the sky, what we have is the error, E. So error of what? Error of the target and the output of the perceptron. So you have the target values and you have the output of the perceptron. What is the difference between them? That difference is the error, right? So we have it over here. Now our goal